So this session we prove the result that gamma of a half is given by √5. So let's see how to give the solution. So from definition, gamma of x is given by integral from 0 to infinity t raised to power x minus 1 e raised to power minus t dt. This by definition. Now, when x equals to a half, we'll have gamma of a half to be given by integral from 0 to infinity t raised to power half minus 1 e raised to power minus t dt, which reduces to integral from 0 to infinity t raised to power minus a half e raised to power minus t dt. Now, to be able to evaluate this integral, we are going to do a u substitution, but then the u substitution will be taken in such a way that it will help us to eliminate the variable variable t into the integrand. So we'll say let t raised to power half to be given by u. Now that I'm picking t raised to power half to be my u, so which means if I square both sides, t alone will be u squared. So therefore, this power of e, I'll have negative u squared. Now from this, I'll have a half t raised to power negative a half dt is given by du. So which means that t raised to power negative a half dt is given by 2 du. So you see, this choice of u has enabled me to get expressions that I can easily replace into the original integral and change all the variable or the integral to be pure in terms of this new variable u. So if I pick this t raised to power negative a half, I join to this dt, then I'll be able to replace that product by 2 du, and then I simply replace this t by u squared from this result here. So therefore, gamma of a half will be given by integral. Now remember, with this choice, when t is 0, limits do not change. When t is 0, then u will also be 0. Also will be 0, 0 square, square root of 0 is 0. And when t is infinity, also u will be infinity. So limits do not change. So it will be meant to be 0 to infinity. So t raised to power negative a half times dt is what will give me 2 du. And then this will have e raised to power minus u squared, and then 2 du. So this 2 is a constant, so I factor it out. I'll have the integral from 0 to infinity of e raised to power negative u squared, then du. So this is what gave me the value of gamma of a half. But then to evaluate this integral, we need now to do what we call some transformation of the integral into the polar form. But before we do that, so we can say, let I be given by twice integral from 0 to infinity e raised to power negative x squared, and then dx, and the same I. So remember, this is what I'm calling the integral I. can as well be given in another variable, twice integral 0 to infinity e raised power negative y squared dy. So note that this integral here has the same value as what I'm calling the integral in terms of the variable x, and also has the same value as what I'm calling this integral in terms of the variable y. So these variables are simply dummy. So we can use any of the variables to suit our case. So this choice, then if I square, so this value I multiply by this value of I, I'll get twice integral from 0 to infinity e raised power negative x squared dx. And then I multiply by twice integral from 0 to infinity of e raised power negative y squared dy. And this product will give me 2 by 2 is 4. So I squared equals to 4 integral 0 to infinity of e raised power negative x squared dx times integral from 0 to infinity e raised power negative y squared dy. Combining, I'll get this as 4 integral from 0 to infinity integral from 0 to infinity of e raised power now e raised power negative x squared e raised power negative y squared, then dx dy. Then using loss of indices, I'll have I squared equals to the integral from, actually these are limits for x from 0 to x equals to infinity, and then y from 0 to y equals to infinity of e raised power I right minus x squared plus y squared, and then dx dy. Now at this point now I go into what we call polar coordinates. So because now I have double integral, now switching to polar integrals, polar coordinates. So remember that in polar coordinates, so I want to carry out my integration in this region. So because, so this is infinity, this is 0, and then this is actually moving towards infinity. This is the y-axis, this is the x-axis. So we want to carry out our integration in this region here. So this region. Because x is running from 0 to infinity, y is also running from 0 to infinity. So this is the region where the integration should be carried out. And in polar coordinates, remember this area element, dx dy, is given by r d theta. And then x is given by r cosine of theta. Y is given by r sine of theta. And then x squared plus y squared is given by r squared. These are the values that helps to convert from rectangular coordinate into polar coordinates. So let me call this one integral 1. This equation 1. Now, the first thing, so where there's dx dy will replace by r d theta. Where there's x squared plus y squared will be replaced by r squared. And then we see that limits of x run from 0 to infinity. Similarly, limits for y runs from 0 to infinity. But remember now the theta, which is the angle. So from this x-axis to the y-axis in this region, the maximum rotation of the ankle is actually 90 degrees, which is pi over 2. So therefore, theta will be running from 0 to pi over 2. But then r, the radius, can take any value from 0 to infinity. So r will take the value from 0 to infinity. So the new limits of integration will be theta running from 0 to pi over 2 or 90 degrees, r running from 0 to infinity. So using these values in polar coordinates, we rewrite the first equation as I squared is given by 4. So remember we had 4 here. This factor of 4. Integral from, so I use theta from 0 to theta equals to pi over 2. And then r from 0 to r equals to infinity. And then at this point, I'll have r d theta, and then e raised to power negative r squared. So that will be e raised to power negative r squared, then r d theta. So with this, I'll have, can write this one as 4 integral from theta equals to 0 to theta equals to pi over 2. And then inside I have integral from r equals to 0 to r equals to infinity of r e raised to power negative r squared dr. And then I have the theta. So let's concentrate with this part. So the integral r e raised to power minus r squared dr, this we use substitution. We let u to be r squared, which means du is given by 2r dr, which means dr equals to du over 2r. So this will be integral r e raised to power negative u times dr is du over 2r. So r and r cancels out. R and r cancels. So we have a half integral of e raised to power minus u du, which is just given by negative a half e raised to power negative u. So which means integral of r e raised to power negative r squared dr is negative a half e raised to power negative r squared. Now, when we put in the limits 0 to infinity, r e raised to power minus r squared will be negative a half e raised to power negative r squared, and then from 0 to infinity. Now the upper limit, so remember this can be written as negative a half and then 1 over e raised to power r squared, and then r from 0 to r equals to infinity. So when you put in infinity, then 1 over e raised to power infinity squared, denominator will be a very large value. So 1 over very large positive value, 0. So we'll have negative a half into 0 minus, when you put r for 0, so it'll be e raised to power 0 is 1, 1 over 1 is 1. So negative 1 times negative a half gives us positive a half. So therefore, I squared will be given by 4 integral theta from 0 to theta equals to pi over 2. Now, this value here, we have gotten the answer to be positive a half. So we'll have a half the theta. Now factoring out a half, we get twice integral from 0 to pi over 2 the theta. Now the theta will be given by integral of the theta, or 1 the theta is just theta, and then theta from 0 to theta equals to pi over 2. So which will be twice into, so upper limit will give us pi over 2, minus lower limit will give us 0. So remember, this is theta. So which will be 2 times pi over 2 is just pi. So which means that I squared, remember I squared was the same as the value of gamma of a half squared, is given by pi. So which means that I alone, which would be now gamma of a half, is given by square root of pi. So I have simply gotten I by getting the square root of each side of this equation. So therefore, indeed, gamma of a half is nothing but square root of pi. So that's how we prove that gamma of a half is root pi. Thank you.